What's the period of the focal pendulum in
Use the 37.7 is a time getting is the latitude, I guess. The time period I found is 49.
Yeah, that's correct actually. That's many of you have just found this. At least 14 hours here.
Yeah.
But you said it correct. You said 37 just now, but then you wrote 15 out here. You're
Okay.
smiling. I'm asking, how come?
Let me check. I think I made a mistake there.
You said it correct, but then your answer is not matched. Build a focal country. If you notice, focal pendulums are always very tall.
Yeah, very tall, because they have to have very long interval or distance, so that it can actually be able to put in the Earth's rotation connection affect the motion.
So once there was a suggestion made by one of my colleagues that make a tabletop focal pendulum, and it might be a popular toy, you might become rich because it will be a very popular toy for giving you prompts.
May apply it on a tabletop, like a
Yeah, or
room
just
table.
this sized focal pendulum, which it should, the principles are the same. It's just the error associated with it will be too large. But if you can have such a nice toy, people would like it.
Yeah.
Right, even with a little bit of fudge here and
See
there.
how,
Yeah.
and you can actually show that, hey, that you can actually prove that the Earth is still rotating.
There you
It's
go.
affecting this.
So there's a homework due today. And oh, someone left. I thought we have a new student again. They posted it for a change. I don't know if they read. So, anything you guys have to comment on? So there was this suggestion I made. It's too warm.
It's to be wrong.
Okay, so there was a suggestion made in the first lecture that with the add drag, if you do if you calculate the time it takes, then I'll excuse homework. And some of you attempted it. I think 3 of you attempted it. So I thought, but I was not satisfied with either of the work. And then I asked something in the midterm related to that. But all that was the time taken for it to go up to reach the top. Like all of you guys did not proceed forward from there. Calculate the time it takes to come down. Okay, so the homework still is applicable. And since we are doing particle mechanics, we can do something else also. So another exercise. So you have this ruler, and you might have seen this demonstration before. It's almost every school would do this. What will happen if I try to bring my fingers closer? If I try to push. So if I do this, what will happen? Have you heard this before?
Eventually the end of the meter stick will either tilt to one side.
No, it will not.
Oh, okay, if you keep your same distance, equally spaced, at same speed, then yeah, it should stay.
So what will happen if I try to move my finger? It will stay.
The same.
What does that mean? Same.
I mean, like, it's not gonna fall.
Why not? So if you notice, okay, so most of you probably have not seen this. So this is the simple one.
It's kind of like a bridge too, because if you have, it's all, the one side will pretty much hold up against the weight of half of the ruler, and then the other will take the
Correct.
hold
Exactly.
up the other.
But what if I start moving it now?
And if you move it at the same.
No, you won't be able to. That's one of the
Yeah,
things
which
that
that's.
you won't be able to move both fingers simultaneously. If you carefully see my fingers, only one is moving at one time. See? Right? And after a while, my right finger will stop and the left finger moves. Now my left is moving. I'm trying to bring both fingers together. Okay. At one time, only one finger is moving, if you notice. Right?
Yeah.
And it will not fall. I'm balancing it. I'm not cheating. And it will always come and meet at the center of mass. In this case, this is a symmetric object. So the center of mass is exactly, if you notice, 50 centimeters. It's uniform. But imagine a broom, which is heavier on the right side, lighter on the right side. It will pick the center of mass.
Even before.
It will not fall. That's an interesting part. Okay, it will not fall. So it will always come and meet at the center of mass. This is, I expected all of you guys to know this. Okay, that's okay. If you have never seen it, now you know that. Then this itself should be interesting enough.
I've done it with pencil here.
Yeah, but now you're balancing at the center of mass, correct?
Yeah.
Yeah, good. Okay, so now here is another thing, so more remarkable than this. Okay, so I do the same thing now. I try to move. My right hand is moving now, and I wait for the point when the left hand starts moving. So now it has started moving. So I measure this. It's at 75, if you guys remember it for me, 75. And now my left hand is moving. And I want to check the point when my right hand starts to move. Okay. So now my right hand has started to move. So it is about, what is it? 27. Okay, so subtract it from 50 each. So 27 minus 50 is 23. So the distance from the center. And the distance from earlier was 75.
75.
75, so it is 23 over 25. And you can keep doing this, next number to next number. Okay, so this number has a meaning. So 23 over 25 will always be equal to, irrespective of who does this, not who, if I use the same skin, same material, skin and the wood, right? So this will be equal to mu k over mu s for my skin, skin dependent, skin wood. Okay. You can do this for metal, wood, any combination of surfaces. Okay. So that should be remarkable. Our constants are hard to measure. This is indeed coming out independent of how you push it. It doesn't matter how you push it. It'll always come out this. So your homework is to derive that.
The coefficient of friction.
Correct. So derive this formula.
Is that homework fixed or another?
This is in the, what is it called, extra credit. It is optional. You don't have to do it, but you can use it to replace your lowest homework.
So what do we have to derive like that?
Derive this. Why is this equal to the length? This is a length, right?
Yeah,
L left over right, let's say.
that is friction.
Yeah, this is coefficient of kinetic friction, coefficient of static friction. Is that clear, the question? It should be relatively easy, easier than the earlier problem that I gave, the time, this thing, except this one is, you won't find it on the internet, probably, I never searched on it. So these days, everything is available, I'll be surprised. But the earlier problem probably is available on the internet, but then it's harder to penetrate because at least what I'm expecting from you guys, I'm expecting an analytical answer, but first at least get an answer, right? And then I'll ask you to get an analytical answer. That I think is not available on the internet. So you will have to do it wrong. Similarly, this one I think is not so popular because just because I didn't hear it doesn't mean that it's not popular. So I was ignorant. Yeah, okay. But it should be interesting in its own sense. So just. And it should not take any more physics than introductory physics knowledge. So, yeah, what we're pointing.
No.
Okay, so we introduced the Lagrangian and the Hamiltonian also to a certain extent. And I have tried to convey to you that Lagrangian problems are common when you have constraints. And I tried to show that the pendulum problem is constrained to move on a circle. So whenever you have a problem like that, where things are constrained to move on something, for example, these are simple constraints like going on a circle. A classic constraint is in electrodynamics, where you say del dotted with B has to be equal to 0, right? So that's a constraint now. If you're doing electrodynamics, you cannot have a magnetic field which does not satisfy this condition, right? So that's a constraint. So you, and often we need to learn how to include constraints into the system. So in the earlier last week, the spirit in which we worked is that we wrote down the Lagrangian, used the equation of constraint, and then got our equations of motion. Now we want to do in a more generic way where the constraint is also there in the problem so that we can get the equation of the constraint also, or for the equation for the tension also in the string. So that's going to be, I'll try to do examples, and in your homework you will see about 2 or 3 examples also. Hopefully it will clarify. So, so let's do the pendulum problem again. So this time Since in your homework, it's a spherical pendulum, let me do spherical pendulum twist. I won't completely solve the problem, but to a great extent, I will catch all the important properties in there. This will be the same spirit in which we will do the Kepler problem also, so it will be can you make it full screen? Oh, full screen, yes. Thank you. And whenever I start cutting it, this you have to remind me, think it will get cut. Okay. So, idea is every object has a kinetic energy. We are usually concerned with systems where potential energy can be identified and written down easily. If you cannot find the potential energy, which is very common, then you're in trouble. So then Lagrangian is not very useful. Okay, so that's a simple way, or you can probably sometimes work on it, but it's not as straightforward as when you have a potential energy expression. And remember, most of the time we don't have a potential energy expression. That's why most of the engineering courses don't deal with Lagrangian. It is only fundamental physics that deals with Lagrangian, because potential energies are very easily available for the interactions that we study. When you're building a bridge, potential energy is not very easy. When you think of a tension, force of tension, the potential energy associated with force of tension is not easy to work with. But at the same time, it's a constrained force. So to a certain extent, it can be also, but then it's not so useful. So you have to trade between how useful it is versus formalism that you use to work with. So I want to start recognizing this equation of constraint and writing equations, and at the same time writing the Hamiltonian also. We have to start with the Lagrangian, work on the Hamiltonian, and work on it, work with Hamilton equations of motion also. So let's think of a spherical pendulum. What's a spherical pendulum? What is a spherical pendulum versus any normal pendulum? Or what's a normal pendulum? I don't even know what's a normal. So,
It's a normal pendulum would be one pendulum just oscillating.
yes, and what's a spherical pendulum?
Spherical would be one that goes around in a circle.
No, like normal pendulum also, we do allow it to go around in a circle, except if it has to be a rod.
Or is it just the actual pendulum is shaped as a circle and that circle is oscillating?
Usually a pendulum, we make it swing in a plane. Like we always choose our initial condition in such a way that it passes through a point. Right, so it is possible that I can push the pendulum in a tangential direction, like it can go in a circle, for example. Is that clear? So maybe. Oh, so for example, this is a pendulum. This is in a plane, but I can always make it go like this, right? So now the freedom is more. There are two angles that it can go in. It's no more in a plane, right? So the first version where everything happens using one angle, I can choose one angle to specify the position of this pendulum. Then it is a simple pendulum, right? That happens in a plane. When it is happening like this, right? Then it is a spherical pendulum. Usually you need two angles. Like it is like on the surface of a sphere at this point. And to specify the positions on the surface of a sphere, you need two angles, a latitude and a longitude. If you have to specify your position on the surface of Earth, you need a latitude and a longitude. Like longitude is what decides our time, right?
Yeah, it's
like-
east to west.
Yeah, we are, what's our longitude? Anyone knows our longitude?
We're looking at this too.
Like 0 is London. And 360 degree
90
is,
degrees approximately. 90
that
degrees.
might be correct, because usually it's 360 degrees. Every 10 degrees is 1 hour. We are probably about 7 hours behind London. So 7 into 10, 70
No, it
degrees, which is
90
about,
degrees.
yeah, it is
It's,
about
90.0. 380.
Yeah, you must be right. Okay, you might be right. So check on quiz. Right. What's your latitude? It's a good knowledge to have. What's our latitude? What's the longitude? Sorry, no, longitude is what I asked. Sorry.
Latitude is 37.
37, very good. So it's good to know your position in case you're lost and you have to save your planet. So at least you should know what your latitude and longitude is. Okay. So now that I talked about the pendulum, I usually don't like to change my plans, but I'm going to change the plan a bit and not talk about spherical pendulum. I think since you guys did a homework recently, it might be more instructive to do a slightly different problem. And let's do an inverted pendulum. So we have seen a lot of pendulums for, so the list of pendulums you've seen is simple pendulum, right? Spherical pendulum, I just now talked about. Foucault pendulum is when you change the position of the pendulum also on the earth. And now there is an inverted pendulum. Okay, what other pendulum? We introduced one more pendulum, no? Or maybe I did not introduce it. Oh, I was supposed to give that as a homework problem. Yeah, I forgot. Again, huh? Yeah. Foucault pendulum we did mention. Cycloidal pendulum. What's a cycloidal pendulum? So this was the homework I was planning to give for this, but then I missed it again. If you have a normal pendulum, this is, I think, very nice. We do know that if you have a normal pendulum, what is the time period of this? 2 pi, or 2 pi times square root of L over G, right? Is that an accurate formula? You said it is not accurate, right? We had this discussion
We
at
had
the
to
start.
use this small angle.
And so we do small angle approximation. Now, the idea is that can you correct this? Is there a design you can think of for a pendulum which will correct this, which will really make 2 pi L over G exact? And the answer is yes. That's called a cycloidal pendulum. This digression, I'll only say it. Cycloidal pendulum. This was, I was wanting to give this as a homework this time. Maybe I'll put it in the exam. Now that I've missed the home. Yeah, so the idea is the following. You know what a cycloid is? Now? Like a cycloid, what is a cycloid? Yeah, put a point on the rim of a wheel, and as it rotates, the path it takes, the trajectory of that point is a cycloid. So that's a cycloid, right? So let's say that's a cycloid. And it is not a semicircle. Okay, it is not a semicircle. Again, quiz maybe. What is the circumference of a cycloid? Quiz. What is the circumference of a cycloid? This length. The circumference of a cycloid. It's just nice to know. It is not 2 pi r. It is what I want to emphasize is that it is not a 2 pi. Invert this, so it will look like this. That's a cycloid. Now, a normal pendulum, as I said, this is L, that's your G, and 2 pi L over G is your time period. If you have, and this depends on the angle. If it is small angles, it works out well. No? What's the point? What is that? This is the inverted pendulum. Maybe this is not really a good inversion, but right. Maybe better. Yeah. Right. So this is the inverted form of that. Now, if you have a normal pendulum, it depends on the angle theta. It works only for small angles, correct? But when it is large, it turns out that the time period varies, it doesn't obey this formula anymore. So this was done by Hoynes, I don't know how to spell it, how to pronounce it, Hoynes. This was done by Hoynes, he was right before Newton, he lived during that period of time. His idea was, can I change the length of the pendulum in such a way that it compensates for the correction made for a small angle? So change the length of the pendulum as it is oscillating in such a way that it compensates for the contribution from the large angle. And he calculated, it was analytically mostly, he showed that this curve, if you have a pendulum like this is tangent here, right? Is that clear? So at this point, it is a rope, so it has actually to follow the curve of the cyclone. As it gets larger and larger angle, that is the smaller and smaller length of the pendulum is free to actually oscillate. And he showed that for this is exact. This is exact. And we can do this calculation based on the knowledge that we have gained in this course. Using the standard mechanics, it is possible to show that. Probably I will use this in your exam if there is a take-home part of it, or else maybe I'll say beforehand that I will make something out of this so that I can make a question around that. So another quiz problem could be list the possible pendulums you can think of. Right, all possible pendulums. We did a lot of pendulums. Something more. Have you missed any pendulums? You should be able to solve this on that. So now I want to do here inverted pendulum. And what is an inverted pendulum? So this is what it is. So you might have again seen this being done when you're young. Maybe you did this. Can you balance this? Right, so you can balance this, right? What I'm doing is a feedback, correct? So now the question is, I'm not going to look at that. This was the feedback, right? So I saw that it is falling that side, then I push it this way. If it's coming this way, it is falling. So that's a feedback based stabilization. This is worked on, by the way, in robotics. You try to do this in engineering departments. But now we are going to ask another problem. Okay. The question is, I don't look at this. There is no feedback. Okay. I only oscillate this using simple harmonic motion with a fixed frequency. I oscillate my hand with a fixed frequency. Is it possible that certain frequencies help it stabilize?
Yes.
Okay. And the answer seems to be yes.
Yes.
Yes. Yes.
I've seen that before where they've actually took an inverted pendulum, oscillated it at fixed frequency.
Now, just because we are not going to
You
be.
oscillate it.
Then we work for the small angle as well. We go to.
Like the idea is that now pendulum is like this, right? This is stable. Right? Now, the point is now it is unstable here, right? So if I don't do anything, it falls, right? Is it possible to stabilize here? Okay, and I will say the way I suggested that I move my hand, the answer is no. It turns out it cannot be stabilized, but there is an answer. Probably you said you have seen it somewhere. So it turns out if you move it horizontally, it cannot be stabilized. Okay, but if you do this vertically, if you do this now, right? And not for all frequencies, there is a very particular frequency. It depends on the length of this rod, that beyond a critical frequency, it will be stabilized. And that's what is called an inverted pendulum. And then it will oscillate here like this. And even if you it is stable. Even if I hit it like this, it will come back at this point. Okay, is that clear what I said? I won't be able to prove this all the way to the end that it is actually stable because it requires mathematical functions that are not that we have not studied, and more than that, the stability analysis is not straightforward. But what we will do is we can write the Lagrangian for this and get the equations of motions at least. So first we will do the horizontal oscillation and write the Lagrangian for it, get the equations of motion. Do the same thing for the vertical motion, write the Lagrangian and get the equations of motion, and at least argue what might be the difference. Why in one case it is happening and in the other case it is not happening. So that's what we will do. That's what we will do, inverted pendulum, or you can say it's a forced pendulum in the sense the hinge is forced to do something. Okay, so let's start with horizontal oscillations. So this is horizontal oscillations. So we have, so that's the center, so that's your X, that's your Y. Let me not say this is X and Y because I want to use X and Y for the mass. That's it. It's understandable that it's X and Y coordinates, and the pivot of the pendulum, usually we start from here, but it's free to move anywhere between here to here, so it is on a line. So let us say it is having a small loop there, and it is hanging off from here. And we force it on a plane. Is that clear? No. So I think it's not clear. Okay. Again. So make it longer. So this is a small loop here, and the pendulum is hanging off this. So that's M. That's your angle theta that we have chosen, and this could be x1. Right, that's a distance x1, and x1 itself can go all the way from A to minus A. So this is moving horizontally. Is that clear? And at the same time, the pendulum is oscillating in the plane. Is that clear what I'm saying?
Yep.
Lakshi, satisfied? Oh, yeah, we will put it, so good point. So we would like, now this is a pendulum where theta is allowed to have any value between pi and 0, let's say. Okay, and we ask the question that if it's a normal pendulum, it is stable about theta equal to 0. So inverted pendulum, the question will be, is this pendulum stable around theta equal to pi? Normal pendulums are stable around theta equal to 0. By stable, I mean if I disturb it a little, it should come back here then. Right? Unstable is if I disturb it a little, it will go away from there. And the idea is that is it stable at theta equal to pi or not? So we have to investigate that. And I'm giving you the answer beforehand because we are not going to be able to do this anyway, stability analysis. For this motion, it is not stable. Okay. But if I do the same thing for vertical motion, vertical oscillation, there is a critical frequency beyond which it gets stable. Again, I think I've introduced Dustin's name repeatedly. There was a classical mechanics course similarly, and I used to have the apparatus for this. You can have a speaker where it oscillates, and I suggested that someone should do this. And Dustin, who is a student here, works in Dipanjan Masundar's lab. He actually built this a pendulum, and within a week he demonstrated that this really happens. That currently the apparatus is with me. If one of you guys want to play around with it, at least I can tell you what is to be done, and it can happen. I can give it to you guys, and you guys can take it home and play around with it. Okay, is that?
Okay.
So it's basically just a simple pendulum, or you have to think about how you want to design the pendulum. You try to oscillate it using a speaker. Like, so basically there's a speaker and then you connect the speaker to a computer. The computer generates a frequency or a sound and that oscillates it.
Pushes on the.
Exactly, exactly. Yeah, okay. So it is possible to do this in a reasonably easy way, and then it's kind of nice to see that it actually is inverted. Okay, our problem here, since you guys did are working on your homework, some of you I noticed that you have already finished the homework. It should make sense with the problems you have worked on. So let's say this is X and Y. This is the coordinate of this pendulum, is X and Y, and that's your length of the pendulum. And when we try to do Lagrangian mechanics, we try to find the equations or constraints governing them. And here the constraint is L is fixed, right? So I recognize that, okay, L is fixed, so I don't have to worry about that. So what are the coordinates? X. So X is in terms of X1. So it is X1 plus plus L sine theta.
So
And-
what- so wait, we're trying, is the syndrome stable of theta equals pi, right?
We are asking the question, is the pendulum stable around theta equal to pi? Right,
Okay.
so that's what my question is, but again, I'm repeating, I won't be able to answer this question. Because I won't be able to do the stability analysis necessary for this. Okay, we haven't just basically studied all the necessary things, and more than that, the inverted pendulum is so sensitive, there's a very small region, so the plotting of that is more numerical than analytical. So you have to get into the numerics for the problem,
Numerical.
numeric analysis for this problem, and you can actually find the critical angle. I can give you the formula for that, like I have played around with this quite a bit because I was interested, so in that sense, I can give you, but I don't think it is instructive to go through the whole stability analysis here in this course.
Okay.
Okay. Okay, so if this is a problem, and maybe I should first state, this is the, if this was free to move, x1, that's our equation, and y would be how much? Since you guys have worked on the problems. Y will be
Minus Y plus theta.
good, so minus L cosine theta, right? Good, right? We also have x1 given to us, so the idea here is, so this is a constraint now. Constraint is that x1, I'm going to force it. Right, I'm forcing this x1. I will say it is being forced with a simple harmonic motion. So A times we can start with 0 maybe. So it is sine. There is some frequency it oscillates with. Right. So let's say it is omega omega forced because it is being forced. So omega ft. Okay. Notice the moment I'm moving it, someone has to do this. So you're supplying energy from outside. So the Lagrangian very quickly translates into Hamiltonian. So that Hamiltonian may not be conserved, or the energy that you associate with the Hamiltonian will not be conserved. So in that sense, the energy is not the Hamiltonian because you have to put in. So it's not a closed system. Is that clear what I'm meaning? So you should expect later on that the Hamiltonian will not be conserved. It will be a time dependent system. Already you see time dependence in here. So you don't expect the energy to be conserved. So that's a conceptual thing that you should keep in mind. So that's your X and Y. So what will be your independent variables, or what will be the dynamical variable you say? Which coordinate in this actually the nature decides? Is free actually if you want. which coordinate among all this x, y, theta, theta, x1 and so on, there is a choice for the system. Angle theta, correct? So x1 I have decided now because I don't have a choice. X and y, there is a freedom there, but there is a constraint of L. So a suitable coordinate is angle theta. Right? You can also pick one of them, X or Y, and then say that I'm going to relate it with that. That's perfectly fine. But there is only one coordinate that is free in this. So whatever you write for the Lagrangian is dependent on that coordinate. Right? So it's a one parameter problem. Like when we do functional derivative, we vary something that's going to be that angle theta. So L is expected to be angle theta, and then you say angle theta dot. So it depends on the velocity and time, and you want to write Lagrangian, and you write it in terms of the kinetic energy and the potential energy, right? So first question you ask is, what is the Lagrangian? And you recognize the fact that it is a parameter dependent on theta. This is our choice. That's your generalized coordinate you typically say. I like to say it is a dynamical variable. Like that's what the dynamics is happening for angle theta. Like I typically use the word angle theta, but most of the textbooks use generalized coordinates. Perfectly fine. Okay, either one you can use, that's okay. Is that clear what I mean? So what I've identified at this stage is that I'm going to work with angle theta. I want to get rid of all other parameters, get angle theta. Right. So I have to write the Lagrangian is equal to kinetic energy minus the potential energy. Right. And kinetic energy is having velocity. So let me calculate the velocity. So x, or let me write that down. So velocity square is x dot square, that is dx by dt, plus y dot. And we are pretending that there is no z. The motion does not happen in the z direction. In general, there's a little bit of z motion also, but we are constraining the motion in the z direction. That's what makes it a spherical pendulum. So you can immediately say what is the spherical version of a normal inverted pendulum that you do. So to get the x dot, so we write dx by dt. So x dot is equal to x1 dot plus L cosine theta derivative theta dot. By any chance, if L was not fixed, L could oscillate. So if it was an elastic string or there is some motion, let us say this is a rod and the mass is allowed to move on that rod. Those are problems that is typically done in Lagrangian. Then you will change the L also. Okay, so those are all possibilities. So currently L is fixed. Like this is a standard problem in Lagrangian mechanics that you have a rod. So for example, this rod, like this is something that I can ask in exam. For example, there is a rod here. So let's say this is oscillating, forming a cone, right? Think of a small ring here, correct? And if I rotate this with the correct amount of frequency, this rod can stabilize, or this ring can stabilize. It won't fall, right? It will just stay there. So those are the motion of a rod constrained to move on, motion of a bead or a ring constrained to move on a rod. These are standard problems that is analyzed using Lagrangian mechanics. But let's not do that here. That was just a digression again. So x dot is this, y dot, which contributes to the velocity, is cosine theta becomes sine theta with a negative sign gone. So it is L sine theta. It's very similar to the equation that you saw in your homework. Velocity square is equal to x dot square plus y dot square. That's equal to 1 dotted square plus that is a cross term, so it is 2 times L cosine theta, theta dot and x1 dot. And when you square these two terms together, there's a sine square theta, cosine square theta, and you simply get L square theta dot square. Okay, so I jumped on a small step, but since you're doing the homework problem, you read through this immediately. So kinetic energy then is equal to half. There's only one mass, so this is m x1 dot square plus half is not there, so it is m plus L square theta dot square and the m, right?
1/2.
Plus half m. Thank you. Potential energy is equal to mgh. So this is mg times the height. Height is so with some help me here. So it is mg. This is the height, right? So it is minus mg. Which so I think it's minus, right? Minus of mgl. So it is mgy. So that's equal to minus mg L cosine theta. How did we start?
The height is like measured from the.
Yeah, good point. Yeah, so I also get confused with that with respect to what am I measuring the height? Typically, if you notice, it is always measured with respect to the ground, like, so there is a ground and mgz, you say. By that, you have chosen the reference as ground. Here, what I'm pretending is that I'm not doing that. So this is, there is a point here, right, at the very bottom. That's going to be my zero in a sense. I can choose any point, it doesn't matter. So let me say this is the point I want to choose. That's my bias I'm having. So then it will be, potential energy will be this height, h. So it will be mgh, right? That should be clear. Mgh is equal to mg L minus L cosine theta. And this is equal to mgl minus mgl cosine theta. A constant out of the Lagrangian doesn't matter. So mgl is a constant, like it does not depend on anything. So when I'm doing this in my head, I did that and I said it is minus mgl cosine, then it is clean. Okay, but I was trying to skip all those arguments, which probably was confusing. But I do get confused with it can be, you can set this to be zero, that's perfectly fine. Then you have to take care of the fact that we are in the negative region, so we are going down. And that is also, that is exactly MGL cosine theta, that's perfectly okay. So in this, I have chosen u is equal to 0 for y equal to 0. Right. And for this, I've chosen u is equal to 0 for this point. I intuitively like this, but everyone has their own biases, but it's not necessary to do this analysis. So if you feel confused about where this is coming, then that is the answer. But every energy that we talk about, for example, gravitational potential energy, 1 over r potential for electrostatic or gravitational potential energy, where is the 0 for it?
Or
So for gravity, mgh, right? There are two expressions for gravity, right? U is one part. Yeah, so U is equal to mgh. That's one expression. And U is also g m1 m2 over r, right?
minus.
So always a potential energy has a reference point, or else say that it is always change in potential energy. You're very safe if you say change in potential energy is this. But usually you don't do that. You say that, oh, that is a reference point. So that's your reference point. So now where is my reference point? where is my U zero? In this case, you set your ground, right? Ground is zero. So U is equal to zero when height is equal to zero. And matches with that. What about this? No?
Would be whenever the relative to the distance r is zero, when r equals. well,
R equal to zero is the center of Earth, no, that's not easy. Very good, it's at infinity. You always say how much work you have to do to bring a charge from infinity, from a mass from infinity, that's that language. And
because
you
it
heard
goes up.
here U is equal to zero for R equal to infinity, very good. Right, so you have to keep that in mind, always there is a reference point that in that derivation somewhere you do write it, but then you forget it afterward. And then it can be, if you want to match these two, for example, it can be misleading if you don't use that fact. So you should always be careful with that, okay. I'm losing time now.
If we consider that,
Uh-huh.
that u equals 0 and y equals 0, then can we still write minus mgy or is it mgy?
Then it is not, yeah, then it is plus mgy, y is minus, very good. Good, thank you, yeah. That's actually better, yeah, maybe, if I write minus mgy, it's wrong. Yeah, good, thank you for correcting. Maybe that's how the whole question started, maybe, you were worried about that? You don't know.
I saw you hand it just like that.
Oh, you're, okay, yeah, because I was thinking along that, yeah, good. Okay, so that clarifies, I suppose, right? Yeah, now the statement is true. Okay, so my Lagrangian then, in terms of angle theta, theta dot, and t, notice there is a t also now, explicit t shows up here. Where is my explicit c? Oh, because x1 dot, right? There's an x1 dot square where x1 dot will have all this omega dot square. So let me write that down. Yeah, for now, let me just write this x1 dot square. Now, let me replace. Sorry, I should have done this there. Okay, x1 dot is equal to omega f a cosine omega f t. X1 is equal to a sine omega f t. X1 double dot is equal to minus omega f a omega f square a times sine omega f t. So I can plug those quantities in. So it is minus omega f square times a sine omega f t plus plus m l omega f times a times cosine theta times theta dot x, and then that's cosine omega f t, and plus half m l square theta dot square. Did I get it?
Is half mx dot square, right? So is omega f a cos some not minus.
First, there's a minus.
This is a double.
Oh, yeah. So just cosine square, you would argue, right? Very good, thank you. So then there is no negative sign. Thank you. Okay. Otherwise, I'll not get my answer. Okay, so plus half, again, m and x dot square, so it is omega f square, a square, and cosine square. Omega f t, thank you. Oh, good. And this is my kinetic energy minus, which makes it plus mgl cosine theta. Let me go this side. So Lagrangian, again, theta dot T is equal to, this is clearly the kinetic energy term, the usual standard theta dot square, so I'm going to move that to the front of M L square theta dot square. What else depends on theta dot? It seems like this also depends on it. So this is plus M L omega F a cosine theta. And then there is a theta dot and omega F t. And there is a time dependent term. M omega 1 square a square. It's pretty much repeating it. And plus mg L cosine theta. Now there are two ways you can proceed. Eventually, it is, since we know that the simple pendulum works for small angle approximations. But here, notice that we are interested in the inverted, so we want to expand around cosine theta equal to pi. If at all we are doing small angles, we have to expand around theta equal to pi. So let's move that whole process of small angle approximation later on, so at a later stage when the equations of motion are. There is no other motion again other than theta. Whatever is the time dependence is part of the Lagrangian itself. So what is the canonical momentum? So that's canonical momentum is L over theta dot, right? Whatever is the dynamical variable associated with the derivative of that is the canonical momentum. So this is M L square theta dot. That's one from here, and that is another from the second term plus M L omega F A times cosine theta times cosine omega F T. Right. I will also need the derivative with respect to angle theta. This is called the generalized force typically. A derivative of the Lagrangian with respect to the parameter dynamical variable you're having, that's associated with the force. In this case, it's called a generalized force because it's an angle theta. It is probably the torque. So associated, you change the angle theta, it will be the torque. X leads to the linear force, angle theta leads to the torque. So this will be the torque equation. But for our purposes, because we are going to use Euler-Lagrange equations, that's just dl by d theta. So that's equal to, there is no angle theta in here. There is theta here and last term. So comments now, yeah.
So, wait, that was the generating force?
Okay,
Is that what it-
now remember that L is equal to K minus U, correct? Usually, not necessarily, K is velocity dependent. And this is position dependent. Correct? So if I were to take the derivative of L with respect to position, right? Typically it is position. This will not see this. It is the derivative of the potential energy with respect to the potential. That's nothing but the gradient, negative gradient of the potential energy. And what is that typically? That's the force. That's a definition of the force.
Conservative force.
Yeah, if it is very good. If it's a conservative force, I can write it as a negative gradient of a potential energy. That's a definition of a force, and that's a connection between force and energy. So derivative of L with respect to position is a force. Derivative of L with, now we are not doing position, we are picking up any favorite parameter I want to work with. That will be called a generalized force. It may not even have the units of force, but it has the same idea of the force. In this case, it will be the torque. A torque, if you notice, doesn't have the dimensions of newtons, right? What is it? Since R cross with F, it is Newton meter, right? It has. Oh yeah, this is a good point, right? You should ask, what is the unit of torque?
Newton's
Meter.
meters, it's radius times force.
Good. What's the unit of energy?
Energy in joules, which is in kilograms, meters squared per second squared.
Is it correct to say that it's Newton times meter? Right?
Yeah, it is.
So would it be appropriate to say that torque can be measured in joules? Like torque has the same unit, right? So is it okay?
Just with an added per second. squared.
So think about it. I think it is okay, but whenever I have discussed this with others, say no, like even books, you would say that no, torque cannot be written in joules. So I don't know. I think it's okay, but ask yourself. Quiz, can torque be measured in joules? What's wrong in it? What's wrong in measuring torque in joules?
It's the same unit.
Yeah, it's the same unit. Why not? Right?
It's-
So that's why, I mean, debate it, or do you see any flaw in it? I personally don't see it. But I have heard it from multiple people, like let's say my colleagues, that
From which it is R, right? Times the distance, force times distance.
so why are there, to begin with, why are there two units? Why do you not use torque and joules? Okay, so that's the idea of generalized force. Okay, so let me proceed so that at least I do the horizontal case, then I wanted to do the vertical case, at least I can get the equation. So, okay. So that was the idea of generalized force, and which is kind of nice pattern to see. Okay. Theta, there is only one place, I suppose, that's the potential energy, and that's derivative, so it is minus mg(L) sine theta. Good. No, there is one more place, right? Sorry. Here also?
Yeah.
Good. So this is helping theta, right? So it is minus L omega F A sine theta. And this is partial derivative, no theta dot. And that's theta dot and omega cosine omega F T, right? Think so. Okay, good. Euler-Lagrange equation, I need time derivative of dl by d theta dot. I'm going to do it in single step, so I'm going to write this equation down. I'm going to write the time derivative here and equate it immediately. So it is time derivative, so it is m L squared theta double dot. Here I can get the time derivative with theta or with this time, right? There are two places. When I do the first one, it is minus m L omega F A sine theta dot cosine omega F T. And now I can take the cosine omega F derivative itself, which is minus again m L omega F squared times A cosine theta times sine omega F T. Well, let me know if I'm making a mistake. Sine theta and minus m L omega F A sine theta dot. Okay. And if you notice, there is a cancellation. Okay, that's right.
Cancel.
M cancels out, right?
That one of L cancels out.
One of L also cancels out, it should, yes, that's correct. Yeah, let's cancel our L also. else, and then, okay, so we have theta double dot. We write that down. That's the next term, right? So
Is
there's,
it anti-direct?
okay, yeah, I was going to divide it out, but.
Okay, then we can do it.
That's good. Omega f square K sine cosine theta naught. Okay. Now, the important point here is that, okay, this is for, I want to tell you the horizontal and vertical also, right? So this is the horizontal situation. Okay, which is what we are going to be doing. If we do the vertical case, this will come out sine theta, which is probably not obvious for you, so it is plus or minus omega f square A. This will be sine theta sine omega f t will be equal to minus g. Okay, this will be for vertical solutions. Okay. At this point, try to expand about theta equal to pi. So we are looking for expansions about theta equal to pi. So small angle approximations again, but first let me do theta equal to 0 about so that it's clear for you. I want to emphasize where the difference lies. Okay. Whenever you're doing small angle approximations, what you do is that each term can have only one angle. You cannot have double angle. So all sine thetas are approximated to angle theta, and all cosine theta is equal to, for small angles, what is expansion of cosine series?
One,
What's the series of sine? Sine is theta minus theta cube over theta factorial. So I want to keep only linear first order. Huh? What about cosine theta? One, and the next one is
Theta square.
good, but I don't want to keep two double order, so that's only one. Right, so when all the cosine gets replaced with one, all the sine gets replaced with here. By any chance, if there are two angles in a term, if there is a sine theta and another sine theta, that's gone because sine theta has a theta, another sine theta has a theta, so that term is higher order, so the whole term goes away. Okay, in double pendulum, you will see this. Like in the homework problem, we only construct the equation. In the next homework, we will start doing small angle approximation. So if there is a sine square theta, for example, right, that is approximately equal to theta square. That's higher order, right? You neglect this, so that's equal to 0. Okay, for small angle approximation, all higher orders goes away. Anything more than a one angle is gone, including the derivative. Okay, so let's do that. Currently, we are doing for theta equal to 0. So in that case, this is equal to L theta double dot. Cosine theta becomes 1, and I want to also divide out. Now let's see. So this is equal to plus G theta is equal to omega f square A. Cosine theta is gone, so that is sine omega ft. Think of your simple harmonic motion. If you often talk about simple harmonic motion this way. And there is a forcing term. If I were to force this is a forced oscillation. Right? There is a simple harmonic motion. And this is a forced oscillation. Right? That's what is happening in the normal pendulum with a forcing, which is understandable here. But now what is this doing? This is for horizontal, right? This is horizontal oscillations. For vertical oscillations, what is happening? It's L, theta double dot. There is a theta from both in here. So this is equal to plus G minus omega F square times A times sine omega Ft times angle theta is equal to 0. Okay, so this is significantly different. This we understand, this is a forced oscillation. This one is not a forced oscillation. How will you interpret? Very simplistically speaking, here the gravity is being replaced. G, which is pointing down, if you have a frequency large enough, this can become negative. So you see the critical frequency coming in. If omega force frequency is larger, so if omega F square A is greater than G, right? That means this term can be larger. That means it will flip the direction of gravity. Things get stable in the direction of gravity. If this is larger, then the gravity is effectively, gravity is negative. It's in the upward direction. Okay, so that's why you have an inverted pendulum concept coming in. Okay, so that's the source of the inversion coming in. You could ask, so is this really true? If you were standing in such an elevator which is oscillating vertically, will you really feel the gravity upward? You'll have to check. So the experiments suggested are grow a plant. Plant usually knows the direction of gravity. Like plant is sensitive to the direction of gravity. The root goes down, stem goes up. So if you were to have a pendulum or a box that is oscillating vertically, will the root go up and the stem go down? Because effectively that's what it should sense. And these are experiments suggested you should. So that's a simple idea. Only the idea, I haven't solved it and shown that it is actually stable there. But that's effectively the concept that I wanted to point. I will stop here. Thank you.